Welcome back to the playlist. In our last video, we broke down the formula for Leibniz theorem and how it relates to product rule. Today, I'm going to guide you through two full examples that will show you exactly how to tackle series solutions for second order linear ordinary differential equations. First of all, what do I mean by second order linear ordinary differential equations? By ordinary differential equations, ODE, it means the function y depends only on a single independent variable s, and therefore all the derivatives such as y1, y subscript 2 are ordinary derivatives, not partial derivatives. So an ordinary differential equation is said to be a second order if the highest derivative present is 2. E.g., when we have y subscript 2, which is equal to 2 d square y over dx square, it is called a second order equation. Now, a differential equation is said to be linear if the dependent variable y and all its derivatives appear only to the first power. That is, there is nothing like y subscript 1 raised to power 2. Also, it is said to be homogeneous if the equation is set to 0. So now, example 3, differentiate n times 1 plus s raised to power 2 multiplied by y subscript 2 plus 2s multiplied by y subscript 1 minus 5y equal to 0. This is an example of second order linear ordinary differential equation. So take note that let's say you have a value of y2 and you want to get to y5. All you have to do is just to differentiate the value of y2 3 times. That is, if I should find the derivative of y2 n times, it is the same as writing y subscript n plus 2. And for our equation, we start by differentiating the first term, 1 plus s raised to power 2 multiplied by y subscript 2. What do? We need to identify our u and our v. So in this function, v is equal to 1 plus s squared. What's the condition? The condition is that v is the one whose derivatives will eventually become 0 after a number of successive differentiation, while u is the one whose nth differential coefficients can be easily obtained. So now for the derivative of our v, our first derivative is equal to 2s. 1 is a constant, it cancels out. So the derivative of s raised to power 2 is equal to what? 2s. Now if you take the second derivative, we get 2, which is a constant, so we stop there. Because when you get derivative of the third derivative is equal to 0. Now for the derivative of u, let me point at it. For the derivative of u, since our u is equal to y subscript 2, so our nth derivative of u subscript n is now equal to what? Y subscript n plus 2. So we go a little bit lower, we find the derivative, we find u subscript n minus 1. So how do you get y subscript n plus 1 as the value? Just substitute n plus 1, n minus 1 into the value of u subscript n. Since u subscript n equal to what? Y subscript n plus 2. If I replace this n by what? N minus 1. So you add them together, you get y subscript n plus 1. Also for u subscript n minus 2, if you do the same thing, the value is equal to what? Y subscript n. Apply it into Leibniz theorem, which says that the nth derivative of the product of two functions is given as u subscript n multiplied by v plus n multiplied by u subscript n minus 1 multiplied by v subscript 1 plus n multiplied by n minus 1 over 2 factorial multiplied by u subscript n minus 2 multiplied by v subscript 2, and you keep adding up in the series until you get to a finite solution. So I will be stopping at v subscript 2, which is the third term in the series, because the highest value for v2 is what? 2. That is a non-zero. So now we just substitute the value. So u subscript n is equal to what? Y subscript n plus 2 multiplied by, I have v here, v is equal to 1 plus s is power 2 plus n multiplied by u subscript n minus 1 is now equal to what? Y subscript n plus 1 multiplied by v subscript 1 is equal to 2s plus this coefficient here. In the denominator we have 2 factorial, which is equal to now 2 times 1 multiplied by v subscript u subscript n minus 2, which is equivalent to y subscript n multiplied by v subscript 2, which is equal to 2. So now these 2 at the numerator cancels out the 2 at the denominator, and we are left with this equation here. So which is 1 plus s power 2 multiplied by y subscript n plus 2 plus this n and 2s. I can write it out and multiply them together as a coefficient, that is 2ns multiplied by y subscript n plus 1 plus, when you open the bracket at this numerator, we have n squared minus n multiplied by y subscript n. So this is the derivative for our first term. Now we'll continue by differentiating the second term, which is what? 2s multiplied by y subscript 1. So for this function now, our v is equal to 2s and our u is equal to y subscript 1. So writing out the derivatives of v, our first derivative is equal to 2 and our second derivative is equal to 0, since 2 is a constant. So we can just stop at v subscript 1. Now for the derivative of u, we start by getting the nth derivative un, or which is now equal to what? Y subscript n plus 1. Since our u is equal to y subscript 1, we just add n to it. And now to get u subscript n minus 1, you substitute n minus 1 into the value of u subscript n, and that gives us what? Y subscript n. Applying this into the Leibniz theorem also, we have u subscript n multiplied by v plus n multiplied by u subscript n minus 1 multiplied by v subscript 1, and that we keep adding up in the series. So we stop at v subscript 1 because that is the highest value that we have in our derivative of v. That is a non-zero, you get. So now when I substitute the value, u subscript n is equal to what? Y subscript n plus 1 multiplied by v. V is now equal to 2s plus n multiplied by u subscript n minus 1, which is equal to y subscript n, then multiplied by v1, which is equal to 2. So we simplify that together, we get 2s multiplied by y subscript n plus 1 plus 2n multiplied by y subscript n. And for our third term, we have minus 5y. So for this function, our v will be equal to minus 5, the constant, and u will be equal to y, which is the dependent variable. So writing out the derivative of v, our first derivative of v will eventually end up as 0, since v is equal to minus 5, which is a constant. So now we just need to get u subscript n also. So the derivative of u subscript n, since u is equal to yn, u subscript n will just be y subscript n. That's it. So applying this to Leibniz theorem, all we need in the series is just the first term, which is u subscript n multiplied by v, and when we multiply that together, we get minus 5 multiplied by y subscript n. Next thing is to combine all the differentiated terms. So for the first term, we got this solution, which is 1 plus s power 2 multiplied by y subscript n plus 2 all the way to n squared minus n multiplied by y subscript n. And for the second term, we have the solution 2s multiplied by y subscript n plus 1 plus 2n multiplied by y subscript n. And for the third term, we have minus 5 subscript n. Minus 5 multiplied by y subscript n. So which equals to 0. In the equation, we also have 0 at the right hand side. So the derivative of 0 is still 0. Now we collect items. I can notice that you can observe that y subscript n plus 1 appears 2 times. And y subscript n also appears 2 times. So we'll just add the coefficients together. So y subscript n plus 2 has just one coefficient, which is 1 plus s power 2. Now for y subscript n plus 1, we have a coefficient of 2ns, and we also have a coefficient of 2s. So that's why we added them together here in a bracket. And for y subscript n, we have a coefficient of n squared minus n, which is this. We also have a coefficient of plus 2n, which is this. And we have a coefficient of minus 5, which is this. So you simplify that to get 1 plus s power 2 multiplied by y subscript n plus 2 plus, now this 2ns plus 2s, we can easily factorize 2s, which is a factor, a common factor. So what will be left in the bracket is what? N plus 1, close bracket, y subscript n plus 1, now plus, so in this coefficient here, minus n plus 2n cancels out or simplifies into what? Plus n. So I now have n squared n raised to power 2 plus n minus 5 multiplied by y subscript n, which equals 0. That's the final answer for example 3. So moving on to example 4, it says that if s is power 2 multiplied by y subscript 2 plus s multiplied by y subscript 1 plus y is equal to 0, show that s is power 2 multiplied by y subscript n plus 2 plus 2n plus 1 multiplied by s multiplied by y subscript n plus 1 plus n raised power 2 plus 1 multiplied by y subscript 2 y subscript n is equal to 0. All they just want us to do is what? To find the nth derivative of this equation and prove that it's also equal to this. So what do? We start with the first term here. We differentiate the first term, which is what? S power 2 multiplied by y subscript 2. So in this function here, our v is equal to what? S power 2. And our u will be equal to the y subscript 2. So we write out the derivative of v, which is what? The first derivative of v is what? 2s. And the second derivative is just 2, which is a constant. So we stop there. And for our u, since u is equal to y subscript 2, our u subscript n will be equal to what? Y subscript n plus 2. Then we'll go a little bit lower. U subscript n minus 1 will be equals what? Y subscript n plus 1. You go to u subscript n minus 2 also, which is equal to what? Y subscript n. So apply this into the Leibniz theorem. All we need is just the first three terms in the formula, which are u subscript n multiplied by v plus n multiplied by u subscript n minus 1 multiplied by v subscript 1 plus n multiplied by n minus 1 subscript over 2 factorial multiplied by u subscript n minus 2 multiplied by v subscript 2. So when I substitute the values into the equation, I have u subscript n equals what? Y subscript n plus 2 multiplied by our v is equal to what? Where is v? V is equal to s power 2 plus n, which is a coefficient, multiplied by u subscript n minus 1 equals y subscript n plus 1 multiplied by our v subscript 1 is equal to what? 2s, which is what I have right now. For the coefficient, we have n multiplied by n minus 1 over 2 factorial, which is equal to what? 2 times 1 multiplied by u subscript n minus 2, which is equals to y subscript n multiplied by our v subscript 2 is equal to what? 2. So this 2 here cancels out the 2 at the denominator. When you simplify that, we are left with, and when you open this bracket, n multiplied by n minus 1, our final answer is what? For the first term, we have s power 2 multiplied by y subscript n plus 2 plus 2ns multiplied by y subscript n plus 1 plus n is power 2 minus n multiplied by y subscript n. Now we do the same thing for the second term, which is what? We'll find the derivative of the second term, which is s multiplied by y subscript 1. So for this function here, our v will be equal to s, the independent variable, and our u will be equal to y subscript 1, which is the dependent variable. So writing out the derivative of v, the first derivative is just 1. The derivative of s in respect to s is equal to what? 1. Now for our u is equal to y subscript 1. So our u subscript n will be equal to what? Y subscript n plus 1. Now we'll go a little bit lower to u subscript n minus 1, which is equal to what? Y subscript n. When we apply this into the Leibniz theorem, we'll write out only the first two terms of the series. So I have u subscript n multiplied by v plus n multiplied by u subscript n minus 1 multiplied by v subscript 1. I substitute my value into the formula, which is y subscript n plus 1 multiplied by, since our v is equal to s, so I replace v by s plus n, which is the coefficient for the second term, multiplied by u subscript n minus 1, which is now equal to what? Y subscript n multiplied by v subscript 1, which is equal to 1. So combining this together, we have s as a coefficient multiplied by y subscript n plus 1 plus n times 1 is just equal to what? N multiplied by y subscript n. We'll do the same thing by differentiating the third term, which is y. So finding the derivative of y n times is just equivalent as writing y subscript n. So what do we do now? We combine all the differentiated terms. We add the solutions for the first term, the second term, and the third term equals 0. So next thing is what? Is to factorize. So we have just s power 2 as a coefficient for y subscript n plus 2 plus, now for the y subscript n plus 1, we have a coefficient of 2ns, which is here. We also have a coefficient of s. So I added that together, that is 2ns plus s. And now for y subscript n, we have a quotient of n raised power 2 minus n. We also have a quotient of n, so I added n squared raised power 2 minus n plus n. And we also have a quotient of 1, so that is what you see here, plus 1. Now we'll close the brackets and multiply by y subscript n. When you simplify this, minus n plus n cancels out as 0. And this one here, you can factorize it. S is common, right? So when you factorize s out, you have 2n plus 1 left. in the what's it called, as a factor. Therefore, x power 2 multiplied by y subscript 2 plus s multiplied by y subscript 1 plus y equal to 0. The nth derivative of this equation is now equal to what? S power 2 multiplied by y subscript n plus 2 plus 2n plus 1 multiplied by s multiplied by y subscript n plus 1 plus n raised power 2 plus 1 multiplied by y subscript n eventually equals to what? 0. So this brings us to the end of this video. If you gain value, subscribe and engage on the channel. To download a free copy of the file, check the description. Bye.